it's based on the base 60 system they had there. Same thing with our clocks nowadays, why there's 60 minutes and 60 minutes, 60 seconds. They would work with problems where they had a couple more unknowns that helped them out with their areas, but that wasn't quite as present in Egypt. So let's take an example of one of these. This is the kind of problem they would deal with. Say I have a plot of land whose area is 55 units, so we'll say square feet. One side of the rectangle, we have no idea what it is. But we do know that the other side is 6 units longer than that. Right, so this poses a problem. When you have two unknown values, you need some sort of system in order to create it. And they worked about it the same way that the Egyptians did. If you have a shape, the best way to find out the area of the shape is to move the shape around. So keep in mind that everything we have here is the same area, it's just going to start looking a little different. So if I have 6 extra units on one side, I'm going to take 3 of those and move it around. So I'm just going to cut half. And what that's going to create, this side over here is going to be our original unknown value plus 3. It was originally plus 6, we took away 3. And this one is our unknown value with the 3 we added on. And the nice thing about this is I can add in one little tiny square there, and I create a square, a larger square. And the larger square, they knew how to calculate the area for, the simple length times width. So if we look at that again, this is how the mathematician would add. The original area was 55. We created it to be this sort of L shape, except for the square that we added in. When we add in the square, this square we said was a 3 by 3, right? Half of the 6 moved over. This is a 3 by 3 square. Multiply those together, you get a unit area of 9. So if I take the 9 that I added in, add it to the 55 that was originally there, I get the number 64. 64 is created by using a square whose length and width are 8. So I can say for sure that this square's entire length is 8 feet long. If this is 8 feet long, because we added 3, the original side must have been 5. And thus they were able to figure out their unknowns. So if you guys think that your class's math problems right now are complicated, you should have lived back then. It's a lot more fun. But that's how they had no techniques. If you take a 108 class, you learn how to solve quadratics using the AC method or possibly completing the square or other ways like that. They didn't have those. So they had to make do. So we moved to another area of the world, about 600 BC. So we're now in Greece. And Greece used the same sort of uses for arithmetic, but they seem to specialize a lot more in geometry. Which is kind of strange to compare it to what we are nowadays, because nowadays we seem to put so much more emphasis on algebra. Right? There's only one geometry class, for example, that's offered here at CLC. That's the 104, and then after that you just have 108, you have pre-calculus, you have calculus, all these very much algebra-based classes. They focus almost solely on geometry. So we're now in Southern Europe, looking into Greece. In Greece, the natural phenomena that happen around the world weren't often attributed to math directly, they were attributed to the whims of the gods, right? You have the Greek god Zeus, or for example, the change of the seasons. Persephone, the daughter of Zeus, halfway throughout the year would go in between staying with her father and Hera up on Mount Olympus to going down to Hades, and then continuously moving back and forth, and that was how they explained the seasons. And when she was up on Olympus, she was happy, and that's why we had spring and summer. When once she went down to Hades, everything started to die. So different things like this, it took a while for them to be able to realize the patterns that involved numbers. And one of the original guys who worked with this was Thales. And Thales is said to be the first ever mathematician or scientist. He began to use math very much for almost exact problem-solving strategy. And he gained his popularity from doing a problem that was, nowadays, would be considered pretty simple if you've taken a geometry class. But back then was incredibly difficult for anybody, and he was the first one to invent it. The pyramids over in Egypt, the pharaoh wanted to know how high they were. So let's think about that for a second. How do you find out how high a pyramid is? You can't throw a measurement down because there's a pyramid in the way, and if you throw it along the side, you only get the length of one of the sides. And this began to stump people. How do you find out the height of the pyramid without simply dissecting it and throwing a rod straight down? And he began to use triangles. He used properties of triangles. Cutting a triangle here. Also, when it later in the day created a shadow, we created another triangle there. And if you're curious as to actually how he figured out the problem, feel free to either ask me after the class or reach out to the geometry teacher back there. I'm sure she'd be willing to explain it to you. But for right now, in the use of time, I'm going to go ahead and move off of that. And just say this is the general idea of how he started to approach things, using problems, creative problem solving. He also began to come up with statements such as the sum of all the angles within a triangle is the same as the sum of the angles of two right angles. So we know that today as all the angles in a triangle add up to 180 degrees. So that's the way that he would look at it. He also said that the ratios of similar triangles had equal fractions amongst every single one of their length dimensions. So moving on from Thales, going into the 100 years in the future, we got Pythagoras. Pythagoras has a lot more popularity than Thales because he seems to have done a lot more. But the confusion is that actually there's argument as to whether he did anything at all. You guys know Pythagoras' theorem, right? Pythagorean theorem working with triangles, right? The a squared plus b squared gives me c squared. And there's actually controversy as to whether or not he created that or he had one of his students. See, Pythagoras was in charge of almost an entire cult of mathematicians. And it's actually probably one of the most fascinating things I've found out through all my research is he was in charge of a cult. And let me give you a couple of these things that they would do in order to be able to participate in the Pythagoreans. That's what they were called. They're dedicated to learning, mostly religion, and they're very philosophical. They never ate beans or beans or meat. They never hunted. They were not allowed to use wool. They dressed in white. They slept in white linen bedding. And they had a common symbol, which is a pentagram. They were dedicated to finding the patterns in nature. Imagine being a person in Greece and realizing that numbers were connecting your world. It's quite powerful stuff. It's pretty easy to believe how people would dedicate their entire lives. But one of the things, if I bring up the Pythagorean theorem, I might as well show exactly how they came about this, because it's kind of a cool way. Once again, a proof used by very older mathematicians without very many techniques. So they went about it like this. Find a triangle, right triangle, whose length I'm going to just label as A, B, and C. So we know that it is a right triangle, which means that corner down the bottom makes a nice 90-degree angle. And I create a square. Now, the square I have just made perfectly so that it can fit, and I can draw three other triangles around it. By the way, I'm very proud of this slide. I just want to tell you guys, it took me like 15 minutes to create this thing from scratch. Anyways, so all I've done is I've created a square, and I put it so that all the right triangles equally match up the sides. The blue square in the middle, right, is a square created by the longest side. So if it's created by the side C, we might as well give it the area of C squared. And that's all I want you guys to keep in mind throughout this whole thing. The blue area is C squared. Because I'm going to start messing with your mind. So I'm going to take this, I'm going to drag it over. And all I'm going to do is move things. Take both the triangles, and I'm just going to group them. Okay. So the blue area has not changed. The triangles have not changed. I've just simply made it look a little bit different. But notice that by making this different, I've now taken the blue area and divided it into two smaller squares. The middle square down here is a square whose length and width are B, so it becomes B squared. And the top one's the same thing with the smaller side A, and that becomes A squared. And what we find out via that is that the area originally created by the longest side, C squared, is equal to the area of the two added together. So talking about Plato, not this Plato. I know every time I say Plato, you guys think this Plato. It's not this Plato. I'm talking this Plato. Plato and Euclid. So Plato and Euclid, once again, continue the idea of geometry. They're both still in Greece. And Plato actually had written upon his academy a large sign that said, let no one ignorant of geometry enter here. So geometry, if you guys want to know how powerful it was in Greece, and the main academy there thought it was almost a priority, a prerequisite to even enter the building. Euclid became famous for later starting to develop geometry so far that he proved everything known to that time. He only took three assumptions to start off with, and that was what is a point, a line, and a plane. So once again, if you've taken a geometry class, they always say how a point, line, and plane, you can't very easily or effectively define it. How do you define a point? A point is a point, a location. You can't really grasp it. So he said, take these three to be, a point, line, and plane. You all know what they are. And he continued to prove everything known about geometry off of just those three. All the properties we know nowadays, or all the properties they knew then, about corresponding angles, vertical angles, if any of these are ringing bells, that's exactly what he proved. And he wrote a book. It became an instant bestseller in the ancient Greek world. And yeah, that's pretty much all I've got for Greece. So Greece, by the way, I keep switching between these different locations because they eventually do a lot, but they hit sort of plateaus. And the mathematical baton gets tossed to a different area in the world. And the next area here is actually quite far away, and that's China. So, focus on the Middle East type area, Egypt, right, Greece. We're going all the way over to China. And China had a lot more similarities to nowadays. They had the base 10 system, which was a little bit different than had been invented in Egypt. So they had the symbols for 1 through 9. But they sort of combined that with Egypt. So they would take sticks, and they would just simply put sticks on the ground, and they would take 9 sticks, throw them together, until they got one group of 10 sticks, put it off in the corner, and then continuously do the same thing with others. So algebra became suddenly easy. Subtracting 1 just meant that I took 1 away from one of the sticks I had placed down. The difficulty where they hit was that after they came up with one number and finished their problem, they would represent it using one symbol. And by representing it using one symbol, they hit the same problem we saw with the Egypt slide, where the moment you do subtraction from that, it's very difficult. So it wasn't very effective, but they did start working with math. And they, once again, also sort of grouped it in with religion and this mysticism. They said that, for example, the number 4 was considered to be exceptionally unlucky, and that belief still holds today in China. It's a little superstitious. The number 4 was very unlucky. The number 8 is considered to be exceptionally lucky, and different things like this started to appear. Another cool one is this idea of a magic square. Have you guys played Sudoku? Sudoku? Anyone? Yes? Nodding? Yeah. Except for the people that are just sort of going out and nothing. No. Anyways, Sudoku, right? The whole idea is that you have to add up the rows and columns to get, you know, the same number. They have to have 1 through 9 equally, and they can't be repeated. This actually comes from China, the game, but also sort of this belief, this myth, that the Gold Emperor supposedly saw a large carp, you know, a massive carp, jump out of the water, and on his back had these numbers on his back. And the nice thing about these numbers is that every single row, column, and diagonal here adds up to the number 15. And off of simply that, they started to investigate, right? That's kind of cool. How can you rearrange just 9 numbers so every single row, column, and diagonal has the same sum? And it began to pique interest and investigation.